So today we start with a new topic, that is IAL spectrum. Now over here, according to your specification, you should be able to use the infrared spectra or the data that is given to deduce the functional group present in an organic compound, or you should be able to predict infrared absorptions if the wave number data are given for functional groups which are familiar to you. So some of them which we need to know are these things. That means you should be able to identify alkane, alkenes, aldehydes, then alcohols, carboxylic acids. So some of the ones which you have come across. So first, the next thing is when you talk about IR, the IR is again an instrumental method of analysis. Instrumental method means you need an instrument like the mass spectrometer you had. Same way, you need a instrument to analyze the substance. The IR stands for infrared. Now these infrared radiations, they have a frequency which is below or less than that of red. So that is why infra means less than red. So if you will look over here, this is our visible region over here. This portion is a visible region over here, which has been expanded in this case. So this is your visible region. Over here, you are talking about the radiations at this level. You're talking about the radiations over here, which are your infrared. So they have a frequency less than the red frequency. And the ones which we use over here, they are called as ultraviolet. So you will study about ultraviolet with spectroscopy, visible spectroscopy in a A2. But here we are using this part of the spectrum. This part is called as a visible spectrum, where we see different colors and so on. So we are talking about the wavelengths or the frequencies, which are basically frequency less than red, or wavelength which is more than, because frequency and wavelength are inversely related. You must have done this in your physics. And why we are saying they have a less energy? Because the relation is E is equal to hc by lambda, where c is the velocity of light, lambda is the wavelength, and E is the energy. So as you can see over here, that if an wavelength is more, energy will be less. And we are saying frequency is below. Frequency, how is frequency related? Frequency is related by E is equal to h nu, where nu is the frequency, So frequency is more, energy will be more. But here for IR, frequency is less, so energy will be less. Now, why we are going into this? The reason is, when you have a molecule, let us say, for example, you have a water molecule and you supply the IR radiation, or let us say some energy. Forget the infrared. Let us say you provide some energy to it. What is going to happen to it? Is the bond going to break? Is the change of state going to take place? Is it going to lose an electron? That depends on what is going to happen. What happens when you supply energy to any molecule depends on the amount of energy supplied. Like, for example, we have talked about this before also. Like, for example, if you have a H2O solid and you provide enough of heat, enough of energy, enough of heat, it may change its state. If you continue supplying more of energy that is equal to enthalpy of vaporization, because liquid changing into a gas, it will change the state. If you still continue providing more of energy, what may happen is the bonds may break. So that would be called as a bond enthalpy. This will be called as a bond enthalpy. While these will be called as enthalpy of change of state. Like this will be enthalpy of melting, because you're changing solid into liquid, and this will be liquid to gas. So this will be enthalpy of vaporization. Now, if you continue providing energy to this, then this may lose an electron. This may lose an electron. So I'm not balancing it, but so then in this case, that energy will be called as ionization energy. Now the problem here is if you have a water molecule, for example, the same thing, and you supply IR radiations, when you supply IR radiations, they are, as explained, they are less energetic. They do not have enough of energy to break the bonds. They do not have enough energy to change the state. They do not have enough energy to remove an electron. So what they do is they can only or I can say that when the bonds absorb energy, not which energy, the IR energy, IR radiations, when the bonds absorb the IR radiations, what happens is they start or they have two effects. They have two main effects. They cannot break, they cannot lose the electron, the atoms cannot lose electron. So they have two main effects. One of the effect is the bonds may start stretching. The bonds may start stretching. That means bond length will change. It may increase or decrease. So instead of saying increase or decrease, I'm just writing stretch. The other thing that can happen is the bonds can bend. So if they are bending, that means the bond angle may change. Bond angle changes. So like, for example, if you have a bond like this, two bonds like this, two atoms attached to here, one possibility is they may start stretching like this. So this is stretching, or they may come close to each other. So both are stretching and coming closer. So it cannot remain stretched. So it will keep on changing the bond length. That is one possibility. And the other possibility is that if there is a bond angle over here, what may happen is they may come closer or they may go away. So the bonds may come closer or the bonds may go away. That means that is bending. So there are many different types of changes that take place, but these are the two mains. That means the stretching and the bending. They are named different way: rocking, scissoring, bending, stretching, many of them. We will now in your IAL specification, we need to focus only on stretching. That means you will be only focusing on what are the stretching vibrations, nothing else. You will be only looking at the stretching. It doesn't make any difference in what we are trying to understand. Focus will be only on the stretching. As you can see in your specification over here, they're just talking about the stretching, not the bending. So we are not going to focus on this. Okay, next thing. Now, as we said, the molecules or the bonds will absorb the energy, and then they may bend or stretch and so on. So what does it result into? What happens to it, first of all? Or so when the bonds stretch or bend, what happens is the bond polarity may change. Bond polarity may change. Now, I'm using the word may change because it depends on the molecule. Now, this is something important. The bond polarity may change. Now, why is the bond? Why are we talking about the bond polarity? The reason is the bond polarity is a vector quantity. It is a vector quantity. It depends on the magnitude, that means the value, magnitude, as well as direction. So for example, if you have a carbon dioxide molecule, and okay, another important thing before we take the example, another important thing is that the IR spectra or spectroscopy, that means the machine, it can identify only polar molecules. Only polar molecules. Now here is the problem. The reason why either this polar molecules, so okay, now here is the problem. The problem is, like for example, if I ask you for carbon dioxide, will this be identified? Carbon dioxide. Now if you, based on our information, we know CO bond is polar because the electronegative difference, but the CO2 molecule is non-polar. But the CO2 bond is non-polar because the dipoles are in opposite direction, or you can say the shape is symmetrical. But the problem is when this carbon dioxide molecule absorbs the IR radiation, it may start bending or stretching and so on. So if it bends, let us say, now before the dipoles were canceling out each other because they were symmetrical, they were equal and in opposite direction. Now what happens is they are at an angle and they cannot, so this becomes unsymmetrical. This becomes unsymmetrical because of, or in another word, you can say the dipoles do not cancel. The dipoles do not cancel. Now, since the dipole does not cancel, it means now in this shape, it is polar. So when the IR radiations are absorbed by carbon dioxide, it becomes polar. And as a result, now it can be identified. Now it can be identified. So even though CO2 is polar, but it can be identified because when it absorbs the radiations, which radiations? The IR radiations, it changes or it becomes polar. And that's the reason why you can identify. Now, using the same concept, if I ask you about CH4, another example, CH4. So if you look at CH4, the carbon-hydrogen bonds are non-polar. So the CH4 molecule is polar. So this is the shape of a tetrahedral shape of a methane molecule. So it is non-polar because the CH bonds are polar, all the bonds are polar. So this is a symmetrical molecule. As a result, the CH4 molecule as a whole is also non-polar. Now, even if it absorbs the IR radiations, the bonds are not going to become polar. The bonds are not going to become polar. The bonds are polar or non-polar. That is based on the electronegative difference. So this non-polarity is due to the electronegative difference. So that is not going to change. The molecule polarity can change because of the symmetrical shape, whether the dipoles cancel out each other or not. So even though the IR radiation is absorbed by the CH4, the angles over here may change because of the bending. Like for example, let us say this CH and this bond come over here, the bond angle changes. but still the CH bonds are non-polar. As a result, this will still be non-polar even after absorbing the IR radiation. As a result, this cannot be identified. So you need to look case by case. What we can understand from here, let's take one more example, like for example, CCl4. CCl4. Now, in this case, the bonds are polar. These are the representation of a dipole. So in CCl4, the CCl bonds, these are polar, but the CCl4 is non-polar. Why? Because this is symmetrical and the dipoles cancel out each other. And the dipoles cancel out. So as a result, the CCl4 is non-polar. But what happens is when it absorbs the IR radiation, what may happen is now it may bend like this. Now the moment it bends like this, so after absorbing IR, due to bending and stretching, stretching, what may happen? The CCl4 becomes polar, and as a result, it can be identified. Why it becomes polar? Because now the dipoles do not cancel. So overall, after taking all these examples, we may summarize it in a simple way, that is, if the bonds are polar, so if I want to a summary for what we have just talked about, which type of molecules can be identified, we can simply say, if you have bonds are polar and molecules are non-polar, then in this case, what will happen? After IR absorption, what will happen? The polarity can change. Polarity will change and molecule can be identified. That is one case. The second possibility is that bonds are non-polar. So the molecule has to be non-polar. Molecule is also non-polar. It cannot be polar if all the bonds are non-polar. In this case, after IR absorption, the polarity does not change. That means it still remains non-polar, therefore cannot be identified. Then symmetrical molecules, diatomic molecules like hydrogen, oxygen, nitrogen, chlorine, these things, they do not absorb IR radiations. Basically, that means the polarity does not change, therefore cannot be identified. A very common question that is given in your exam is, they may ask you, you are given CO2, CH4, H2, Cl2. And they may ask you which of them can be identified using IR. Now, the important thing is all of them are non-polar. All of them are non-polar. But we know only for carbon dioxide, the bonds are polar and the molecule is non-polar because of the shape. So in such a case, it is only this thing that can be identified. Only the carbon dioxide can be identified. Now, another thing is how do different molecules, or do all molecules absorb the same amount of energy? No. The amount of radiation absorbed, that means you can understand it this way. Let us say you have two weights attached to the spring. So these weights can be considered as atoms, and this can be considered as a bond. Now, how much force you need to pull this spring is, that depends on the weight over here. If they are heavy, you need more weight over here to pull them. You need more force over here. If these are light, then you need less force for this spring to move. Exactly this. So exactly the bond length or bond. So exactly the same way over here, the amount of radiation absorbed, the amount of radiation needed or absorbed depends on three things. The length of the bond, that means the bond length of the bond, then the atomic masses of the atoms attached, and the strength of the bond. Now, how are these helpful for us? Like for example, if you have a carbon hydrogen bond, you have a carbon Cl bond, you have a carbon oxygen bond. Now, each of them will absorb different amount of energy. Each of them will absorb different amount of energy. The reason is, so here, each bond type requires different amount of energy to vibrate. Vibrate means the bending or stretching. And that depends on, why different amount? That depends on these things. That depends on this thing. Now, if you go to, so we have understood the basic concept of IR, what the IR does. The bonds absorb the energy, they are not able to break, so they vibrate. Vibrations are different types, bending, stretching, and so on. How much energy they will absorb, that depends on the length, the atomic mass, and the strength of the bond, and that decides how much of energy it will be absorbed. Now, once the bonds absorb the energy, if the polarity changes, or if the molecule is already polar and the polarity changes, then it can be identified. And if the polarity is not changing, or if the molecule remains non-polar, it cannot be identified. Now, moving on to the actual IR spectra. How does the IR spectra look like? We don't need to go into the IR spectroscopy, that means the machine which is used the inside of the machine, just like we did for the mass spectra. We don't need that. So first of all, let's look at how does the IR spectra looks like. How does the IR spectra looks like? Now, IR spectra looks like this. Now, there are a few important things over here. The the IR spectra is given to us in this form. Now on the y-axis you have a transmittance. This is transmittance. That is a way to measure the amount of radiations that pass through the substance. Sometimes they give you this, sometimes they will give you absorbance. That means how much of energy is absorbed by the bonds when a radiation falls on. You don't need to worry about that. No one is going to talk about it. The y-axis will be either transmittance or absorbance. No problem with this. The second thing, on the x-axis, you have the wave number. On the x-axis, the wave number, and the units for this is per centimeter. The units for this is per centimeter. Another interesting thing you will observe over here is the smaller number is on the right side and the larger number is on the left side. Usually, we are used to like a smaller number over here and then it increases this way. But here it is opposite. Again, this is out of our syllabus. We don't need to worry about that because this will be given to us. The next thing is these numbers may not be in a sequence. So it's not like fixed numbers like difference of 1000 or 2000. Or there's no such. You just need to read this. We are going to focus on these peaks. What we are going to look at is these things. Where are these peaks? That is more important for us. So the actual transmittance values are not important. The actual transmittance values are not very important at this stage. That means at the A levels where we are talking, it is not important for us. The intensities are important. The intensity is important. Now, how is the intensity related to what we are talking about? That means transmittance or absorbance. If there is a weak intensity, then what happens is it means there is less absorbance. Absorb radiations are less. Most of them are transmitted. High transmittance. High transmittance. And so if you will observe over here, high transmittance means the value, the peak will be small. Most of the, if on the y-axis you have transmittance. And if the intensity is high, it means that if you have the transmittance, it will be low transmittance. That means the peak will come up, down over it because lower values are over here. So the peak will come down like this. So that depends on what you are looking at, transmittance or absorbance. You don't need to worry. You just need to look at the values given over here, but I'm explaining to you. So is this opposite? That is what we need to understand. And if you have a high intensity, then it will be high absorbance, or you say low transmittance. This is just right now only for our understanding or just to know it. We are not going to use them as such. Maybe they will give us in a multiple choice, so we need to understand it. That's the only thing. Now, what are we going to use this for? Means how is the IR spectra going to help us? Now, yes, before that, this area that is around 500 to 1500 per centimeter, this one, that means from here to here, this area, it is known as a fingerprint region. This has been asked in the exam, the wave numbers for the fingerprint region. Now, this is like all human beings, they have some fingerprint, but there is slight differences. We may look similar. We all have hair, all have one nose, all have two ears, and so on. So we are very similar to each other, but still our fingerprints will be different. Same way over here, you may have two alcohols exactly the same, but there still will be some difference due to their bending vibrations. So this actually the fingerprint region, it is due to the bending vibrations, which we are not focusing on. If you remember, I showed you the specification. We are only looking at the stretching. So you should only know this value, 500 to 1500. This value, this range is known as a fingerprint region, and it is due to bending vibration. At this stage, we are not focusing into this. At this stage, AS level, we are not going to look into this. Next thing, what are we going to information from basically? Information from IR spectra. That's the main use of the IR spectra. Till now, we were only trying to understand what is IR, and how it works and so on. Now, what information are we going to get from here? The first thing is, which is the most important thing, is it helps us to identify the function group. Identify the functional groups. The next thing is, it can help us in predicting the absorptions in the spectrum of organic substances. Like, for example, if I know my organic substance is an alcohol, so I can figure out which, because of the OH, I can figure out where its absorption peak will be. Because the OH in carboxylic in alcohol will have a absorption at a specific wave number, while the OH in carboxylic acid will have an absorption peak at a different wave number. So based on that, we can predict where the absorption peak will be. And the third thing is we can also find deduce the structure of your organic substance. So you can also find the structure of the organic substance if you are provided, if the wave numbers, that means the on the x-axis, the number that, and the molecular formula is given. The molecular formula is given. So if this is given to us, we can even find out the structure of any organic substance, because we know there are isomers. Like, for example, you can have a, let us say you have an alcohol, C3H7OH. This is an alcohol, yes, CH3, CH2, CH2OH, 5, 6, 7, 8. Okay. 5, 6, 7, 8. So that is correct. So if you are given this formula CH3H8O, now this can be an alcohol, it can be an ether. So how can you figure out? Or if you are given an aldehyde, and a ketone, so they both have the same aldehydes and ketones. Aldehydes and ketones, both are isomers. Both are isomers, but their functional group is different. So how can we figure out? So we can use the IR spectra to exactly figure, which we will not do basic for aldehyde and ketones, we will not do that. But at a higher level, you can figure out. So let's try to use them. Now, you will be provided with the data booklet. There's two things over here. The first thing is you will be provided with the data booklet where these values will be given to us. You don't need to memorize it. You don't need to memorize this. Now, there is a value over here for bending. This. You are not going to use this. We are going to use this stretching vibrations, stretching, stretching, and stretching, and here stretching. So this will be provided in your data booklet. You don't need to go and memorize this. These are the values provided to you in your data booklet. So in your exam, ask for it. Even when you are practicing, try to use this. That's one thing. The second thing is the major functional group that we will be using are these. So you don't need to worry about whether it is stretching or bending. You don't need to worry about that at all. This is main functional groups, which is required according to your marking scheme. So let's see how are we going to use this. Now, right now, I'm taking some of the spectra from different websites. So we may not have the exact values because these values are provided from your Edexcel board, but we will try to understand how to read an IR spectra and identify the molecule. So let's say I have this molecule spectra. This is a, let's say this is an spectra of an unknown molecule, and I want to find out what is this functional group. Basically, I'm identify the functional group. Now, before you go and identify the functional group, we need to understand that if you want to know whether alkene is present or not, or your organic compound is an alkene or not, you will try to find out if there is a peak or there is a peak for the wave number corresponding to C double bond O. That means you will search for a peak for C double bond C in alkene. That means you will be searching for a peak at this region. If there is a peak at this region 3095 to 3010, it means your organic compound is an alkene. If you want to search for an alcohol, then you will search for the peak for OH at this region. So you are going to identify a substance based on their functional group. If I want to search or identify whether my substance, organic substance, is an alcohol or not, I will search for the peak of OH at the given wave number. That is by looking at the wave numbers from the data booklet. If I want to know whether it is an aldehyde or a ketone, then I will search for the C double bond O, that is a carbonyl. However, if I want to search for carboxylic acid, if I want to search for whether my compound is carboxylic acid or not, I will search for the peak at C double bond O as well as the peak due to OH. So I will be looking at two different things. I will be looking at the OH peak for carboxylic acid and the C double bond O peak for carboxylic acid. That means if you go to the data booklet, you will find there is a OH peak for carboxylic acid at 3300 to 2500. That is the OH peak in carboxylic acid. And then you will also go for the carboxylic acid. You don't study aryl right now. Aryl is benzene, so you don't need aromatic. Then you will search for this peak also. So the CO. So you will search for two peaks for carboxylic acid, the C double bond O peak, and then you will search for the OH peak in carboxylic acid at this. Once you have these both the peaks, you will know that your substance is carboxylic acid. If it is not, both the peaks are not present, it means it is not a carboxylic acid. So let's try to use this like over here. Now, if you look at the alcohol peak over, if I want to find out what is this substance. Now you will observe over here, there is a peak somewhere around, the values are not very clear, but there's somewhere around 3000. The values are somewhere around 3000. Now, if you will look at these values, according to this, because this has been taken from different source, here, the peak is somewhere between 3,200 to 3,550, while in actual practice, the alcohol is somewhere over here, 3,750 to 3,200. So this is approximately here. So this can give us an idea that this is a peak due to the OH. But OH peak is also present in carboxylic acid, so I should search for this. I should search for this. Now, the C double bond O peak, the C double bond O peak is somewhere around 1740 to 1720. Now, 1740 to 1720 is somewhere around here at this region. C double bond O should be here, but the C double bond O peak is absent. Now, since it is absent, it means it is not the carboxylic acid, it is alcohol. Why alcohol? Because it has only the OH peak. You have only the OH peak, not the C double bond O, so it cannot be carboxylic acid. It is not an aldehyde or a ketone because the C double bond O is not present. Let's take another example. Let's take another example. Now, if you look over here, the OH peak is usually over here, both for the carboxylic acid and the OH, both for the carboxylic acid as well as the carboxylic acid as well as the alcohol, because the alcohol peak. Okay, let us take the whole thing, because now if you will look over here, the alcohol peak is around 3,750 to 3,200, and for carboxylic acid, the OH peak is around 3,300 to 2,500. So it should be somewhere around this region, which is 3,000, somewhere over here. And there is no peak for this. This is a peak for C double bond O. This is a peak for C double bond O, which should be somewhere over here, 1740 to 1720. So what does that mean? In this case, the OH peak is absent, while you have a C double bond O peak at. Now, the important thing is you don't have to look at the values from the mass spectra. You don't have to draw it, use the scale, and no need to do all this thing. Once you get an approximate idea that this is a C double bond O, you will specify this value. This is the explanation, 740 to 720. So when they ask you to identify and justify, this is identify, and this is justify. That means the explanation. Why do you say that this is a C double bond? So identification is you are saying it is a CO peak for an aldehyde and a ketone, and the reason is there is a peak at 1740 to 1720, which the values you will always pick from the data booklet. Then if I take another example, now if you look over here, now this is a different spectra. Now you are getting a peak somewhere over here, that is OH peak around the same area, and you also have a C double bond. So you have a OH peak and you have a C double bond O. So this gives us an idea that this is carboxylic acid. Now once you know this, how will you justify? Now justification will be based on the values from the data booklet. You already know it is a carboxylic acid, so you will pick the values. You will pick the values from the data booklet for the carboxylic acid. So you will say there is a OH peak for carboxylic acid at 3,300 to, this is a reason for this, and the C double bond O, again you will pick the C double bond O peak for carboxylic acid, because there's a difference for an aldehyde and a ketone. Both are slightly different. So you will pick the value for the carboxylic acid, and that will be your justification. That will be your justification. Finished. So based on this, you say your substance is carboxylic acid. Now, let's try to do another question based on this to understand it slightly more. Now, this is given to us. So as we said, a molecular formula is given to us. The molecular formula is given to us as C3H6O2. And the mass spectra is given to us, and they are asking us to identify this substance. To identify this substance. So identify the organic substance compound. How are you going to identify this organic compound? Now it's very easy based on what we have just seen. This is a OH peak and this is a C double bond O. So that means your organic compound is carboxylic acid. The organic compound carboxylic acid, and they want the reason. The reason will be, the justification will be this thing. This will be your justification. But this is not the end of the story. You have identified it is a carboxylic acid, 3,330 somewhere over here to 2,500 somewhere from here. You don't need to measure it from the spectra, and this is 1725 somewhere from here to 1700 to 1725. It's a narrow peak. We will talk about for the OH group. So you know the carboxylic acid, but they said identify the organic compound with this molecular formula. Now, so you make up the formula now. It means you already know that it is an organic carboxylic acid with 3 carbon atoms. So which means it should be CH3, CH2, COOH. So this will be equivalent to C3H6O2. Now, why we are saying a carboxylic acid? You would say it is already 2 oxygen atoms. So we know it is a carboxylic acid, not necessarily, because with this formula, you can also have an ester. You can also have an ester with this formula. So this is an ester, and this is a carboxylic acid. So from the IR spectra, we were able to identify that my molecule is carboxylic acid. It is not an ester because it contains the OH peak for the OH and the peak for C double bond. Another question where they can mix both the IR and the mass spectra is here. Now, this is taken from some past paper. So they have given you the alcohol already. They have given you the alcohol that is C2H5OH, and they are asking us to prove that this is a mass, justify this is the mass spectra of C2H5, and this is a IR spectra of this molecule. So they are asking us to can be analyzed such as mass spectra, the mass spectra of the. So there were many questions related to it, but I'm just talking about justify that the mass and IR spectra given is for C2H5OH. That is what we have to do. Now, the first thing is you will look at the mass spectra. Now, from the mass spectra, we figure out that this is your molecular ion peak. Why? Because it is maximum m by z value. So this means this relates to the MR of the substance. So the mass spectra is for a molecule which has MR of 46. So let us look at whether C2H5OH has a mass of molecular mass of 46 or not. 12 into 2 plus 5 plus 16 plus 1, so 24 plus 5, and this is 17 over here. So this will be equal to 46. So this clearly shows that the MR is for the C2H5OH. That's one thing. The next thing is we have to look at the IR spectra. We have to look at the IR spectra to figure out whether it is actually the alcohol or not. Now, in this case, they have given us the values over here in the question itself, so you don't need to look at the data booklet. Now, I want to prove that this is an alcohol. That's the main thing. We already know it is C2H5OH. So we need to find out whether it is an OH or not. So if you observe over here, there is a OH peak, this one, while around 1700 over here, the C double bond O peak is absent. So this clearly shows that this is a IR spectra of a molecule with OH group, as there is a peak at 3750 to 3200. 3750 to 3200. Finish. So that proves that your molecule is C2H5OH. So mainly you will be identifying the molecule based on the wave number. That is what you have to do. That's the main thing for the IR. And this finishes your IR spectrum. You need to practice more questions. That's the only thing. So it is a correlation of the wave number with the functional group or whatever they are asking us. That's the only thing we can do. We can stop here now.